scaling up your analysis from laptop to HPC. And the idea is that you have some data analysis running on your laptop or desktop, and now you want to move that over to Expanse or another HPC system. How would you do that? So here is the outline. So first we talk about, when it's, and is it actually worth to run on Expanse? And then the most important one is, how do you set up a portable and reproducible software environment that you can move from your laptop to Expanse or vice versa? Give you some more tips about running JupyterLab on Expanse. And then we're getting into the meat of it. We're talking about how to scale up your calculation using multiple CPUs or GPUs. And the example we are using is a Python-based example using Python-based data frames. And then we ask the question then we measure parallel efficiency to see how well we're actually using multiple cores. And then finally, I mentioned a little more about how you can get an Expanse account yourself. Okay, so when do you want to run things on Expanse? So first of all, your laptop or desktop is the best environment to do any coding, to write your own code. Good for the exploratory phase of a project, if you have small data sets and you can run on a single or a few cores, but then eventually you run out of resources and then you want to go to Expanse if you have large data sets or many data sets, long runtimes, and then you can take advantage of multiple cores or GPUs. Basically, use your laptop if your data fit into memory and the compute time is sufficient, then there's no reason to move to Expanse. But if your calculations take too long or you need more memory or both, then it's a good time to move to Expanse. So the first thing is, if you have software running on your laptop or desktop, how do you move that over to HPC? And I mean with moving over, meaning using the same exact environment and moving it over to HPC. And why is that important? As you know, it's very difficult to reproduce anybody's work. That is for experiments, but it also applies to code. Unfortunately, you would think that code would give the same results in any environment. Unfortunately, it does not. So here are some definitions. I won't go into this about reproducibility, basically getting consistent results no matter how you do it. Reusability, basically using your code to get new results. And today we're going to talk about scalability, using the same code, but scaling it up to larger data sets. So there are a number of tools that help you create reproducible infrastructures, and that includes Jupyter, because there you can combine the documentation, the code, and the results all in one document, so that helps. If you want to get reproducible results, you need to version control your software, so that's where Git and GitHub comes in, and you already heard a lot about that. But then we also need to set up a software environment, and yesterday Marty talked about singularity containers, and today I will focus on an alternative, which is Conda. And if you write Jupyter notebooks for your research, you may want to look at this paper that we wrote a few years ago. There are some tips about reproducible research in Jupyter notebooks. But let's talk about how to set up a software environment that's both reproducible and that's portable. Let's say from your PC or laptop to Expanse. So which environment you want to choose, Conda or Singularity? So if you're a beginner, or you already have experience with Conda, that will be a good choice. If you're in the exploratory development phase of a project, if you have frequently changing dependencies, so it's very easy to compose a new environment in Conda within minutes. And Conda environment has some limitations. Generally, you would run that just on a single node, but which is not bad. They have 128 cores, and it's supported on almost all OSs. And it runs on your native operating system. On the other hand, maybe you want to use Singularity container. If you're an advanced user, you already have experience with Docker containers or Singularity containers. You're interested in setting up a production environment. Now, Singularity containers are often set up just for a single tool, as you know, and you already use them during this workshop here. We have optimized container for Expanse, such as PyTorch, TensorFlow, etc., etc. And so they have been specially optimized to take advantage of the hardware. They support also multi-node calculations. One downside is they're only supported on Linux. So if you want to run Singularity on a Mac or Windows, you need to install some virtual machine. But one advantage of Singularity is that you package the entire operating system with it. So it's really very reproducible. But as a beginner, or if you're more in exploratory development, Conda is much easier to use. And it's not either or Conda or a container. You could start, developing a Conda environment and then put that into a Docker container to productionize that. All right, so what is Conda in case you have not used Conda? So let me first talk about reproducibility. So if you think about scientific research, usually, people publish a paper. Many times these days, you are required to publish your code, hopefully also some of the data. But when it breaks down, it's usually the software environment. I'm sure you have tried to install software that other people have developed. You have a hard time to installing it or running it. So that's where things break down. And that's where Conda is really helpful. First of all, Conda is a system to install your software. I'm sure many of you, if you program in Python, have used Conda to install packages such as NumPy, Pandas, etc. And one thing it does, it checks dependencies of any pre-existing packages that it needs. But with Conda, you can also set up a portable software environment. That means you could have two different environments running on your same computer, or move it from a laptop to Expanse, for example, with the same environment. It runs multi-platform, supports many languages. And so why do you want to use Conda environments? Maybe as a beginning Python user, what you used to do, you just install packages as you need, using either pip installs or Conda installs. But after a while, you will notice you're going to run into some trouble here, because there are going to be version conflicts, errors, and basically non-reproducible results. The idea of a Conda environment is that you have isolated environments. So on the same computer, you could have one environment that uses, let's say, Python 3.7 and those versions of software, another environment that uses Python 3.9 and another version of software, and those can coexist and there are no conflicts about it. Furthermore, you can take those environments and move them from your laptop or desktop to Expanse and run them there. And that's what I'm going to talk about today. Okay, so how do you define a Conda environment? A Conda environment is defined in a YAML file, environment.yml file. Typically, you would put them at the top level in your Git repository. This is the repository that we're using today here, and in the top level, there's a file called environment.yml, and this is the way you define your environment. First, you give it a name. Generally, it's a good practice to use the same name as a Git repository. Then some channels, that is basically the repositories where you download your packages from, and the order here matters. And then you need to specify what software package should we import here. So we need Python, JupyterLab, etc., etc. And to make it reproducible, a good practice is once you have a final version that you want to let other people use, to what's called pin the version numbers here. So it's reproducible. Use the same version over and over again. Moreover, one advantage of Conda is you can not only install Python packages. For example, in our later example, we're using PySpark. PySpark needs Java, so we also install here OpenJDK. So here we install Java 11. Now this is independent of the Java that you already installed on your machine. So you could have a different version of Java, and this one here is completely independent environment here. You can also specify environment variables in this file here. So for example, PySpark needs a few configuration parameters, which I've already set up here. Okay, so how do you create a Conda environment if you have not used Conda before? First, you need to install usually mini Conda that gives you the basic Python environment and frequently used packages. And once you have installed that, then you can say Conda environment create, and you give it the name of your environment.yml file. But if you're a Conda user, you know that Conda can be slow if you have lots of dependencies. So there's a new kit in town that's called Mamba, which is much faster. So I suggest try Mamba instead, which will be much faster. So that's how you create your environment. And then if you want to use it, you say Conda activate, name of environment. and then you're ready to go. You run JupyterLab or any other Python application, and when you're finished, you deactivate your environment. Now, this all works very well on your laptop, Mac, Windows, Linux. Now, if you try to do that on Expanse, you will see this is going to take a very long time. And the reason is that your home directory is on a network file system. So this will install, thousands of files in your home directory, and that will be extremely slow. And fortunately, we have a solution for that. You just use the Galileo script, which will take care of creating your Conda environment automatically. So don't do this actually on Expanse, but rather use a Galileo script. So how does it work? So let's go into some details. So first of all, since this is not an in-person meeting, I want to get some feedback from you. And we're going to use Zoom for that. So on Zoom, under reactions, there are two choices here, yes or no, and we're going to use them today. So if you completed a task, please, click yes. Or if you don't want to follow the examples, just click yes right away. So I have some feedback that, okay, we can continue because we don't have much time. If you have a problem, turn on the no flag and then go to Slack and report your problem there, and we'll see if we can resolve it. So please use those so I get some feedback. I don't want to waste time. We don't have much time left. Okay, so the first thing is I want you to log in. So if you do not have not logged into Expanse yet, just go ahead, use either SSH or use the Expanse portal and log in with your training account. And then once you have a terminal window open, then use the reactions in Zoom to say yes, that you have an open terminal. So let's go ahead. If you don't want to do the exercise, then please say yes right away so we can see how things are going. Okay, I already see one green here. 4. Okay, there's some thumbs up. Let's wait for a minute here or so. I want to make sure everybody is logged in. And again, if you don't want to follow don't want to run the examples, just say yes anyway. So I just know that I can continue. All right, I think in the interest of time, I need to go on here. You can always do the exercises later yourself as well. So, which partition should we use? So, for many of the exercises so far, we gave you a script which basically did that choice for you. But I structure my talk in such a way so that when you get your own, let's say, startup account, you know what to do. So you can refer to this presentation. So if you want to run JupyterLab on a CPU, use a shared partition if you run less than 128 cores, which I usually would do for a Jupyter notebook. It probably doesn't make sense to run that multi-core. If you run your notebook on GPU, use GPU shared if you use less than 4 GPUs. But one thing to keep in mind too is sometimes you just want to quickly test something or you have a very short run. Then you can use the debug or GPU debug partitions. You can only have one job running in those, but that's a really quick way to get onto a node. Otherwise, if you choose any of the other ones, you're going to wait longer in the queue. Okay. All right, so here's just an example how you would use Galileo, and you have used that a lot, but this is the idea. Let's say you're on your own, you have your own account. This is the way you would do it. First, you need to add the path to Galileo, and you can put that into your bash profile file. We have already done that for your training account, so don't do that. Then you clone a Git repository, you launch your notebook with a Conda environment. Let's see how that works. You already submitted jobs with a container environment, but now we're using a Conda environment. So the only difference is that we're saying here's an option called Conda env, and this is the name of the Conda environment, and Conda YML, which is a path to the environment.yml file. And then for good measures, we add member to speed it up. So this is your recipe basically to use a Conda environment on Expanse. And yeah, you copy that, as you know, copy that URL in your browser. So don't do this. This is just in principle how this would work if you do this yourself. Now, creating a Conda environment takes time because Galileo creates a Conda environment on the fly. That may take a few minutes. So instead, you can also create a packed conda environment. And there is a shell script in this df parallel Git repository called pack, and it creates basically a packed conda environment, which is a tar.gz file. And once you create it, then you can just use it, and you run Galileo this way, where you basically specify, instead of the YAML file, you give it the conda pack file with the conda pack option, and then the path to this tar.gz file, which you can keep in your home directory. So we're not going to do this today. I just want to mention that in case you use that same environment over and over again, you may want to create a packed environment. And again, it may not always work, so that's why I call it work in progress, but that's something you consider. So one other thing I want to talk about in terms of launching Jupyter Lab, you already know how to launch Galileo, but one important part is when you are finished with your work. Important thing is when you're finished, you go to the file menu in Jupyter Lab and you go to shutdown. If you don't do that, your process will continue running. Let's say you requested 4 hours of time. Unless you shut it down, your process will continue running and you burn through your allocation. So at the end, always go to shutdown. You may not have done that during the training, which is okay. But once you have your own allocation, this is your money that you're burning if you don't shut this down. So that's something to remember. So we're going to run through a few data frame examples here. One is we're going to run pandas, Dask, and Spark data frames. If you would run it and those run on CPU. So this is the way that will be run. We say we want to have 10 CPUs, 20 megabytes of memory, 1 hour. And then we specify the name of the environment and the path. And if you want to run the same thing on GPU to enable the CUDA data frames, we say, okay, we run that on 10 CPUs, 1 GPU, 92 gigabytes of memory for 1 hour. But in this case, we use a different conda environment for GPU, which is called df parallel GPU, and it has a different YML file as well. Again, don't do that. This is just the recipe for you how to run things on CPU and GPU. Okay, so now we come to our first task. So we're going to launch Jupyter Labs. So go to this link here. And their description, what you're supposed to do, you basically just launch Jupyter. So we're just doing task 1. So clone this Git repository and then copy this Galileo launch command here. The way to copy that is to click on the side here, this button. That's how you copy that. So launch Galileo. And once you get the once you get the Jupyter Lab URL, paste that in a browser, and then you're done for now. We just want to launch this now, and then I'll continue while the job gets ready. And when you're finished, again, turn on the yes flag so I get some feedback, when to continue. Any questions about this task? So while this, job is launching, I'm going to go through what we're actually going to do. So we're going to talk about scaling up calculation on CPU and GPU. As an example, we use a data analysis with data frames. So if you're a user in R, you're probably familiar using R data frames. If you're a Python user, I'm sure you have used pandas data frames before, but they have some limitations. So I want to try to overcome those limitations. Let's talk about pandas data frames. So pandas data frames basically represent tabular data in Python. But the problem is pandas data frames are limited to the available memory. So if you're running on a laptop, let's say you have 16 gigabytes, you're going to be limited to that. If you have larger data sets that don't fit into memory, you will get an out of memory error. So fortunately, there are some libraries available that can overcome those issues. And one of them are the Dask data frames. So Dask is very simple. It takes basically your data and it breaks up a pandas data frame into partitions. So it breaks it into multiple smaller pandas data frames. So that resolves the issue of handling large data sets. Now you can, run terabyte data sets even on a smaller computer. But so basically we can run out of core data sets larger than available memory. But now that opens up also the opportunity to run basically process in parallel on each of those partitions here as well. No, Dask supports only a subset of the pandas API. So if you're used to pandas, not all the options or arguments are available. So there are some limitations to it, but this is a way to overcome very large data sets plus being able to run those calculations in parallel. So that's one way you can use Dask on CPU. The other one, this slide almost looks identical, but now we're talking about processing large data sets on GPU, and we'll do both. So NVIDIA has developed a GPU-powered data frame library, which is called CUDF or CUDA-DF. But again, it's limited to the available memory. So for example, on Expanse, we have the V100s, and they have 32 gigabytes of memory. So you're limited to that. So if you have less than 32 gigabytes, CUDA-DF will just work fine. If you have more, you're gonna get an out-of-memory error. And that comes to the rescue again, as before. Basically, we can split up this large CUDA data frame into multiple smaller CUDA data frames, and then has the advantage we can then, for example, process things on GPU, run things in parallel, and process any large data sets. And again, unfortunately, CUDA doesn't support all the options of pandas, but it has a limited subset of pandas. So there are two options running either on CPU or GPU. Okay, so far, very often when you deal with tabular data sets, you probably have them in a CSV file format or TSV file format, and those are okay, but they are slow because those are text-based formats. Now, if you really want to do high throughput computing, you may want to choose a different file format. And for data frames, one of the best options is to use Parquet. What is a Parquet file format? But let's first talk about CSV files. In a CSV file, data are arranged in a row-by-row fashion. So when you read a CSV file, you need to read each row to get the data you need. In a columnar storage format, data are organized in a per column fashion. For example, let's say row A is a set of dogs, row B, those are the cats here, for example. And let's say your analysis only needs the cats. I only want to need column B. Parquet lets you read just column B and ignoring columns A and C, for example. So that's called vertical partitioning. Then in addition, Parquet can do a few more things. It can do horizontal partitioning. Let's say I don't like black cats, and I don't want to do calculations with black cats. I can eliminate them as well without ever reading the black cats too. And then if we combine the two together, so basically I read only the data that I need. So how does that work? So horizontal partitioning here uses statistics. So, Conda, Dask, for example, will break up your data frames into a partition, into smaller sets. And for each of those sets, it will calculate minimum, maximum statistics. So let's say you have a floating point value. If it's within the range, then it will use the data. If it's out of range, it will skip the data. That's one way. So Parquet files have metadata. They allow this horizontal partitioning. So how do you use that in practice? So when you later look at the notebooks, you will see this code here. So this is how that works. Let's say I don't want to read all the columns in a Parquet file. I can say I only want to read those 7 columns here. So there's a data set with gene information, which we'll be using today. Here it has many columns, but I'm only interested in those 7 columns. So that's the horizontal, that's the vertical partitioning. So we're choosing columns. But then we also only want those rows where the gene type is protein coding. And the way you do that I'm sorry, this should actually say pandas here. So in pandas, you say read Parquet file name, and then you specify the column names here, and you specify your filters. The same in Dask and CUDA-DF, exactly the same syntax. So then we also have the Dask CUDA-DF. It has a filters option, but I couldn't get that to work. For some reason, doesn't work or it's not fully implemented. But you can do the vertical partitioning and pass in the column names. And then I do the filtering as a post-processing step where I say I only want the G instead of protein coding. We also will look at Spark data frames. I think Mai talked about Spark data frames. Spark data frames also allow vertical and horizontal partitioning, and it works like this. You say, read this file, select the columns, and filter by this. Now, this looks like it's 3 separate steps, but as you probably heard, Spark initializes lazily, so it will actually only read the data that it needs. Okay, how do you create a Parquet file? The easiest way to create a Parquet file is with Dask, and it would look like this. Let's say you have in my case, the file we're using today is a TSV file. So we use the CSV reader input file name, and we say it's tab separated. And then we just say to Parquet output file. There's a few options. You want to have a metadata file there and save it. So what do you get? So a Parquet file is actually not a file. It's usually a directory of files. So this file G or directory geneinfo.parquet is actually a file that has metadata information. And then, as we talked about, this is broken up into partitions and smaller partitions, and the default partition size is 64 gigabytes. However, if you save it on disk, it's actually smaller because Parquet also adds some compression to it. But in memory, those partitions are typically 64 megabytes large, and they are processed in parallel. So important point, Parquet files are really not files, they're generally directories. There's one more thing we can do here, and that is we can partition our data. So here I have one more argument, partition on gene type. So gene type is really an enumeration. There are only 12 different gene types here. And if I specify that, it will create subdirectories. Later on, we will only be interested in protein coding. So instead of reading all the other data, it can just focus on protein coding. And that obviously helps with the query efficiency. And again, you can partition on multiple columns here, not just one. Okay, so we're getting closer to actually running some of the notebooks and comparing their performance. But let's quickly review the different data frames. So many of you probably know Pandas data frame. They run on a single core, then don't run in parallel. And they generally run out of memory if you don't have enough memory there. There are some workarounds, but I'm not going to talk about those today. On the hand, can run things because it breaks up that Pandas data frame in multiple smaller data frames. Therefore, it can run in parallel, and it can run on very large data sets. Spark is the same. Spark just has a completely different syntax from Pandas and Dask. But again, it runs in parallel, and any size. You can have terabyte data sets, can process them even on your laptop. Now, CUDA-DF runs on GPU. It runs in parallel on GPU, but again, it's limited to the available GPU memory, so it will run out of memory. And that's where Dask CUDA-DF comes in, which again splits this up into multiple CUDA data frames and runs both parallel and out of core. All right, so now let's do a little comparison. So we're going to compare the runtime of 5 of those 5 data frame libraries at the first step. And then we're going to look at the CUDA data frame and run it with a CSV and a Parquet file as input to see how the performance is. So let's go to GitHub to task number 2. So by this time, hopefully your notebooks have launched or Jupyter Lab has launched. So for me, let's have a quick look here, see my Jupyter. So in this DF parallel, navigate to notebooks. And then let's see, where were we? The first step you need some data files. So the first step, once you get to notebooks, run this notebook that will copy the data files into the local scratch disk on your CPU node. So that's step number 1. If you don't do this, or everything else will fail. So that's step 1, get the data. Once you're done with that, then run those 5 data frames from Pandas to Dask, CUDA-DF. And you will see at the bottom of each notebook, it will print the runtime. One important thing is when you run those notebooks, don't go through it step by step, but just use this run all button or the fast forward button that will run through all cells in your notebook. If you don't do that, your timings may be off. So that's step 1. We're going to compare those 5 data frames and give you maybe 5 minutes or so for then I'll go through it too in case you don't want to run this yourself. And once we have done that, we want to compare reading CSV versus Parquet files. So we're going to go into the 5 CUDA data frame, and we change the file format from CSV to Parquet, and we run it again and see what the runtime is. And then the important part, when you're all finished, remember, you need to shut down your Jupyter Lab to not waste resources. So you go to File, Shut Down. And then when you're finished again, click Yes, so I know that you're finished. So that's the task for you now to do. So please go ahead, and if you have any problems, put a note in chat, please. I'm sorry, into Slack. Okay, so for those of you that don't run those tasks, let me run them as well. But if you do it yourself, just keep running your own version here. So the first step is we need to run this notebook here, which just copies the data files that we need, which is one CSV and one Parquet file. So let's do this. So the file we're downloading is really not that large of a file. It's 5.4 gigabytes, I believe, to make it faster for the tutorial, so we don't have really big data now. Okay, 5.4 gigabytes for the CSV file. And as I mentioned, the Parquet file include compression, so they are 1.5 gigabytes on disk. So now that we have the 2 files, we can go through the different data frames. We do some data analysis here. So again, we want to use this button here to run through all cells automatically. And let's have a quick look what this does. So we read a CSV file here, and this is where we read the data. So this is for the pandas data frame. You're probably familiar with that. If you read a CSV file, you can also pass in the columns, and it's a TSV, it's a tab separated file. And we read Parquet file, we pass in the column names up here. That does the vertical partitioning. And then we also run in the filters, where we can do row-wise filtering as well. And then we just do some simple data manipulation. We group the data by what is called here the taxonomy ID, and we count how many there are. And then we sort by that count. And finally, we display that information. And let's just wait a minute to see. And then we print out a few results, just so we know that all of the data frames give the same result. So it's reproducible no matter what method we are using here. So this should take about a minute or so. Yeah, so here you see how this data frame looks like. Each row is one gene, and taxonomy ID is an identifier of an organism, and those are different genes here. So we are grouping the data by taxonomy ID and then counting the number of genes for each taxonomy ID. And then we finally sort that in a descending order. And then we display the result here just to quickly check we get the right numbers here. There should be about 20,000 human genes. That's correct. And those are the top five organisms with the most genes here. And the runtime was 56 seconds. So that was 1 minute for 5.4 gigabytes of data. So that's not bad. Let's go to Dask now, which can run this in parallel. And the code looks pretty much the same. I'm not going to go through it. There's some minor variations to the syntax, but it's pretty much the same thing. So let me run the Dask data frame now. Let's see how long that takes. And let's also make sure we get the same results here. Okay, we got the same results, and it took 15 seconds. So that was about 4 times faster than using Parquet, because it could parallelize some of the calculation. Remember that actually the most time consuming part is reading the files. So, the scaling is somewhat limited that we can do here. Okay, let's go next to the Spark data frame and run that. So again, Spark runs in parallel. Now, the thing about Spark is it has a completely different syntax here, how you read the files and how you process the data. but the idea is the same. And again, we get the same results, 14 seconds. So it's about the same as Dask. Okay, so those 3 data frames were running on CPU. Now let's do GPU data frames. So we're going to CUDA-df. Let's run CUDA-df. Again, the syntax is very much the same as you had for pandas. Oh, and you see it's already finished. It only took 3 seconds to run this. So that's pretty amazing. You know, you read in a 5.4 gigabyte file and you do a little data manipulation. You can do that all in 3 seconds. So that's pretty amazing. At least I find that amazing. And, you know, if you have really big data sets that does not fit into the GPU memory, then you would run Dask CUDA. And let's run that one as well. Now this will split up that data frame into multiple partitions and run each one separately. And this will actually create some overhead. As we will see, this is actually now getting slower because there's some overhead, you know, basically running this in parallel. Now, as long as your data fit into memory, just use CUDA-df, don't use Dask CUDA-df. I'm just showing that here, you know, how to do it. All right, so this is, you know, so far we have only used CSV files. Let's do one example where we change things. So here we were reading in a CSV file. So let's instead read a Parquet file here. So we're going to change this file format to Parquet and run this again. Again, this is now the CUDA data frame using Parquet. Remember before it took about 3 seconds to run this on GPU. And yeah, surprise, 1.5 seconds. So it actually cut that in half by just using, you know, a different kind of data frame here. I mean, using different file format. So that shows you the power of using the Parquet file format. Okay, and that ends the demo. So hopefully many of you were able to run some of those examples yourself. And all right, so here's a little summary. So on pandas, it took about a minute, Dask and Spark around 15 seconds, CUDA about 3 seconds, and Dask was actually a little slower. But you know, if you get to larger data sets, you will find out eventually pandas will run out of memory here. So here we have an input file, 43 gigabytes, that was too large for pandas to handle. Here with CUDA-df, using this data set was already, it ran out of memory. But then if you use Dask CUDA-df, it can handle that very efficiently. And that's pretty amazing. Here you have a 43 gigabyte file. You can process that with Dask CUDA-df in 19 seconds. So that's pretty amazing to me. All right, so a little comparison here. But you know, how well did we actually use the different cores? So that's where parallel efficiency come in. So on the first day, Bob Sinkowitz was talking about Amdahl's law and measuring parallel efficiency. So that's what I did. Let's see how efficient we are. So first of all, let's look at the overall performance of those data frames. And let's just take the small data set of 5.5 gigabytes, which actually takes in memory. It takes up 15 gigabytes because a lot of string or character data strings in Python, they take up a lot of memory. So in memory, it's actually 15 gigabytes. And this comparison is on a single core on a single GPU. Obviously, the single GPU, you know, is faster than any of, if you run it on one CPU. So that's what you see here. In general, you see Parquet is much faster than CSV format. There's one exception, the CUDA Dask CUDA data frame currently has some problem with Parquet, so ignore that. There's something wrong with that CUDA reading the Parquet files. I'm not sure why that's happening. It should not be. So the bottom line is, you know, GPU data frames can be extremely efficient, plus Parquet also helps you now to bring down your runtime as well. Okay, now let's scale it up to a larger data set. So now I took that small data sets and made 16 copies of it. So this file size is now 87 gigabytes here. And let's just run it on a single core again. First of all, you don't see CUDA anymore. Why is that? Because it ran out of memory, you know, so you can't run this big size on a CUDA data frame. That's why you don't see it anymore. But Dask CUDA is able to handle that since it splits it up. But interestingly, just using Parquet on Spark actually beats the CUDA here, which is kind of interesting. Now let's run the same data set on 16 cores here. And again, you see that Spark running on CPU actually beats the single GPU here. Okay, so that's that. So important bottom line is, GPU, although it's fast on a small data set, if it fits into memory, if you need to split it up and so on, it's not necessarily that much faster. In many cases, you can just do the same on CPU. And again, try to use Parquet files if you use that same data set over and over again. Parquet is a good choice. So how does it actually scale? Those examples I had, they're mostly reading data. They don't do much computation, therefore they don't scale that well. But let's see how well they scale. So you have seen in Bob Sinkowitz's presentation, the way you do the scaling plot, you have time on the y-axis and the number of cores on the x-axis, and you have a log scale here. So this is a log 10 scale. On the bottom, I have a log 2 scale here, going from 1 to 16 cores here. And let's look at the small data set that you processed here, the 5.5 gigabytes. So the dashed line, this is the theoretical speed up you should get. In reality, you see if you get to 8 cores, it already diverges quite a lot. But as you get to bigger data frames, like the one with almost 90 gigabytes, you see you get a better efficiency out of that. It's still pretty good up to 8 cores and even 16 cores. It's still pretty acceptable. And see how the time goes down. We're going from over 1,000 seconds down to about 100 seconds. And this is for Dask using CSV. And then we can do those efficiency plots that Bob showed us, that basically shows the utilization of the cores. So if you go to 1 core, you have, 100% utilization of the core. If you go to 2, you lose something, still in the 90% range. If you go to 4 cores, you get lower. And you see, larger data sets obviously benefit from more cores. But if you have a small data set, it doesn't make sense to run it on 16 cores. Your efficiency already going down to 50% here. If you want to see how I actually did those plots, the notebooks are available. There's an interactive benchmark, and there's also a batch benchmark available. You can look at those notebooks, how I create those plots here. Now, how about the GPU data frame? Now, as it says, a GPU data frame works on GPU. So if you increase the number of cores, it basically does nothing. Actually, for small data sets, your CPU, your total runtime actually slightly goes up if you use too many cores because you're creating overhead. But what happens if you have very large data sets, having, let's say, 2 cores is actually beneficial here. You see it actually cut the runtime in half, because even though it's a GPU data frame, it still utilizes the CPU too. But it doesn't scale. It doesn't need many CPUs, just a little bit. All right. So, but then the question comes. You can look at those plots, but how do you decide how many cores should I actually use for my job? And I came up with the following idea, which is probably not the best, but that's the way I thought about it. What is actually the cost of running your job? The cost of running a job is the number of cores times time. And then I normalize it by the size of the data set. So, but unfortunately, with this formula, you always favor a single core, because on a single core, you have 100% efficiency by definition. That favors a single core. But as you know, time is money. So there's an opportunity cost. If you wait too long, you want to get your work done faster. So I define a variable called opportunity cost. And it's an adjustable parameter. I just set that to 1 in this example. So we take this cost here and we add another term, opportunity cost times the normalized time. And if you plot it, it looks like this. So for the Dask data frame, running using the CSV file format, you see for the small data sets, the optimum seems to be about 4 cores. And for the larger data sets, the optimum seems to be around 8 cores. And if we use Dask with the Parquet data frame, the story changes a little bit. It actually, for small data sets, it seems like it's satisfied with just 2 cores, whereas for medium-sized data frames, 4 cores is optimum, and for the large one, it probably uses 8 cores. So that's one way maybe to think about it. But the situation is a little more complex, because we need to think about how are jobs actually charge on Expanse. And let's review how jobs are charged on Expanse. So let's first think about running on CPU. So this is a typical launch command. Let's say we're using 10 CPUs, 20 gigabytes of memory for half an hour. How much does it cost? So one CPU or 2 gigabytes of memory, whatever is larger, you will be charged 1 service unit. Now, since we're using 10 CPUs and 20 gigabytes of memory, this job will be charged 10 service units per hour. But since we're only running it for 30 minutes, you will be charged 5 service units. So you need to remember that you cannot just look at the number of CPUs because they depend also on the memory. Now, you're also being charged for the memory, so you need to keep that into account as well. Now, how does that work on GPUs? So here we say, okay, for the GPUs, we use 10 CPUs, 92 gigabytes of memory, 1 GPU for 30 minutes. So on a GPU, the counting is different. So 1 GPU or 10 CPUs or 92 gigabytes of memory, whatever is larger, are charged 1 GPU service unit. So this job with 1 GPU will be charged 1 GPU hour per hour, 1 GPU service unit per hour. But we're only running it for 30 minutes, right? But there's a catch, because the minimum charge for any job is 1 service unit. So that's also something to keep in mind. So this job, although it only runs for 30 minutes, you still pay the charge for 1 hour, which is 1 service unit. So when you think about scaling, you also need to think a little bit about, how you're being charged here. So that's another in consideration, and how much memory you need for your job. Okay, so let me see how we're in time. Actually, we're probably pretty good. So getting ready to use Expanse. So a few people already asked about how can we get access to Expanse. So you can apply for a trial allocation or a startup allocation, or if you do need a larger allocation, you can submit a proposal. There's only one catch, is that the Exceed system will switch over to a new system called Access on September 1. So we're in this transition period. So look at this link to more information and announcement how this is going to change. But I showed you how you can do performance. So you can get a trial account and you can do some performance evaluation. You can use some of my code, look at those, create those performance statistics, and they will help you, submit a good proposal if you need a large allocation and justify why you need to run this, let's say 128 cores. So in summary, I showed you, where does it make sense to run on Expanse, how to set up a portal and reproducible software environment, in this case using Conda, and how to run some tips, how to run Jupyter Lab on Expanse. And then we showed you how you can use, how you can parallelize data frames using CPUs and GPU, data frame libraries, how to measure efficiency, and a little bit how to get accounts. Okay, so here's some homework for you. I said, this is a portal environment. Now let's do the other way around. We know this works on Expanse. The question is, does this DFL work on your lab or desktop? So that's your homework. Try to install it on your laptop or desktop, and then try to run the CPU examples. They should work. And you can also run some of the performance statistics, see how it works compared to Expanse. And then the most important thing is, once you get this working, then you really have a template, how you can apply this now to your own work. And I would like you to commit yourself in the future to write portable and reproducible code. And with that, we come to our acknowledgements. Marty helped me a lot, and Mary, Scott, and Bob. And this was funded in part by an NSF cyber training grant. So any last question? Again, if you try to do your homework and things don't work, feel free to email me, because I'm interested in why things may not work. I claim it will work on both Mac and PC and Linux, but you never know. So that's the end of my presentation. And sorry for going a little bit over time.